a massive structural failure, a mid-air collision, a sudden catastrophic engine blowout. When you picture a commercial airline disaster, you almost always picture something, violently obvious.
Right, yeah. You definitely don't picture a piece of cracked solder.
Exactly. A tiny microscopic flaw in an electrical joint. I mean, something so small, you'd need a magnifying glass to even see it.
But that is exactly what we're looking at today.
Yeah, welcome to the deep dive. I'm glad you're here with us. Because today our mission is tracking the exact timeline and the mechanical cascade of Indonesia AirAsia Flight 8501.
Which was an Airbus A320-216 that tragically crashed into the Java Sea on December 28, 2014, taking 162 lives.
And we aren't just going to look at the timeline of what happened, right? Today's deep dive is about walking you through the flight minute by minute to really understand why it happened.
Yeah, to really grasp how a microscopic crack takes down a 60-ton airliner, you have to look at the environment where this sequence begins.
Right. Set the scene for us.
So it's early morning. They're taking off from Surabaya at 05:35 local time, heading for Singapore. And the departure is, it's entirely routine.
Nothing out of the ordinary at all.
Nothing. By 05:49, they reach their planned cruising altitude, a flight level 320, which is 32,000 feet. The autopilot is engaged, the autothrust is managing the engines, and the crew is just, settling into the cruise phase.
But sitting down in the electronics bay is that unseen flaw.
Exactly. It's located inside a module that controls the Rudder Travel Limiter Unit, and it is quietly waiting to initiate a chain reaction.
Now, if you're listening to this and wondering how a minor electrical flaw in a single component causes a modern jet to just fall out of the sky, you have to understand aeroelasticity.
Right, the aerodynamic forces.
Yeah. At 32,000 feet, this plane is traveling at hundreds of miles an hour. The rudder is that massive vertical flap on the tail that controls the yaw, the left and right nose steering of the plane.
And if you fully deflect that rudder at high speeds, the aerodynamic forces hitting that broadside of the tail are immense.
It can literally snap the vertical stabilizer right off the fuselage.
Which has tragically happened in other aviation disasters. So to prevent that, Airbus uses a rudder travel limiter.
Okay, so what does that actually do?
Well, as the plane flies faster, this system physically restricts how far the rudder can move. It's a vital structural safeguard. So when that cracked solder joint briefly interrupts the electrical connection at exactly 06:00, the system recognizes a fault.
And it alerts the pilots, right?
Yeah, it throws an amber advisory on the Electronic Centralized Aircraft Monitoring System, the ECAM. The message basically says there's a fault with the rudder limiter, and a minute later, a master caution chime sounds in the cockpit.
Which means the aircraft has essentially lost both channels of its rudder travel limiter. Okay, let's unpack this. What did the pilot do when that alarm went off?
He responds exactly by the book.
Mm-hmm.
I mean, the ECAM screen doesn't just show the problem, it gives the pilots the solution.
It's like a built-in checklist.
Exactly. The required action is to reset the Flight Augmentation Computers, which are known as FAC1 and FAC2 via the overhead panel.
So he just turns them off and on again?
Yeah, he turns the push buttons off, then back on. The system reboots, the connection is reestablished across that cracked solder joint, and the warning clears.
And the flight just continues normally. I mean, the crew even contacts Jakarta Air Traffic Control a few minutes later, around 06:11, to request a slight leftward deviation to avoid a weather system.
Which is a perfectly standard maneuver. But the physical reality of that solder joint hasn't changed. You've got the vibration of the aircraft, the temperature changes, it causes the connection to sever again.
So the alarm comes back.
Right. At 06:13, the exact same chime sounds, the exact same amber message appears. They have lost the rudder travel limiter again.
And they execute the same reset, right? The system comes back. But this repetitive failure introduces a massive psychological factor into the cockpit.
Oh, absolutely.
It reminds me of dealing with a glitchy home Wi-Fi router. The first time your internet drops out, you just unplug it, plug it back in, wait for the lights, and move on. You don't even think about it.
But the second time, the third time.
Exactly. By the fourth time your connection drops, you stop trusting the reset button. You start looking for a more permanent fix because the annoyance is just driving you crazy.
But the difference, of course, is the environment. I mean, frustration with a router in your living room leads you to buy a new router. Frustration in a cockpit at 32,000 feet leads to improvisational troubleshooting.
Which is terrifying, and this ties directly into the maintenance history of this specific aircraft, doesn't it?
Yeah, it does. This exact rudder travel limiter fault had been occurring with rapidly increasing frequency in the days leading up to the flight.
So this wasn't a new issue.
Not at all. Ground maintenance crews had repeatedly tried to diagnose it. They ran computer tests, they reset systems, but they never physically found that microscopic crack on the electronic card.
So the crew of Flight 8501 essentially inherited a chronic, unresolved hardware disease. They were being forced to treat the symptoms mid-flight.
Which brings us to the psychological breaking point. Just 2 minutes after the last reset, at 06.15, the fourth failure occurs.
The chime sounds again, the master caution glares.
Right. But this time, the pilot in command abandons the ECAM checklist. He decides not to push the overhead buttons. Instead, he reaches for a different solution entirely.
Wait, what does he do?
Well, he remembers seeing a ground engineer address this exact fault while the plane was parked on the tarmac.
Okay.
The engineer bypassed the overhead buttons and went directly to the physical circuit breakers, the CBs, for the flight augmentation computers.
He pulled the breakers.
Yeah, the engineer pulled the breakers, cutting hard power to the computers, and then pushed them back in to force a hard reboot. And the pilot decides to apply this ground maintenance technique in the air.
Wait, he pulled circuit breakers mid-flight. Why would the system even allow that if it's dangerous?
What's fascinating here is that you actually want pilots to have access to circuit breakers because of the risk of electrical fires.
Oh, right. Because if a component starts short-circuiting and smoking?
Exactly. The crew needs a physical way to sever the power to that specific system to save the aircraft. The danger isn't the presence of the circuit breakers, it's the sheer gap in the procedural documentation.
Meaning the manuals don't cover this?
Pulling the FAC circuit breakers in flight is absolutely forbidden by Airbus. But the manuals don't explicitly detail the catastrophic domino effect that will follow if you do it.
Wow. So it requires a deep engineer-level understanding to know what's going to happen.
Right. The manuals assume airborne pilots will follow airborne checklists, not ground engineer procedures. He applied a ground maintenance fix to an airborne environment.
And because he pulled those circuit breakers, the aircraft's internal logic fundamentally changed. It instantly handed control back to a startled crew.
Yes. Let's look at the immediate fallout at 06.16. The electrical interruption to the FACs triggers multiple master cautions.
And the big one here is that the autopilot and the autothrust disengage.
Exactly. The flight augmentation computers don't just manage the rudder limiter. They are a central hub for flight envelope protections. They calculate airspeed limits, they manage the yaw damper, and crucially, they feed all this stability data to the primary flight computers.
So when he pulls those breakers, he cuts the data feed.
Yes. The autopilot suddenly has no reliable stability information. An automated system cannot fly blind, so its programming dictates an immediate disengagement. The computers essentially threw their hands up and hand the physical control of the aircraft back to the human crew.
Here's where it gets really interesting. Because of this, the flight control law reverts from what Airbus calls normal law to alternate law. Can you translate this for us? What does this actually mean for the pilot holding the side stick?
Well, think of normal law like a modern luxury car packed with safety features, lane keep assist, automatic emergency braking. The computer actively prevents you from doing something dangerous.
So if you try to pull the steering wheel into a wall, the car fights you.
Exactly. In normal law, if a pilot pulls the side stick all the way back, the computer will only pitch the nose up to a safe limit. It actively prevents a stall.
But they just entered alternate law.
Right, and alternate law is like suddenly reverting to a 1970s muscle car with manual steering on a sheet of ice. Those invisible safety bumpers are gone.
So the computer just stops second-guessing the pilot's inputs.
Whatever you tell the side stick to do, the control surfaces on the wings and tail will physically execute, even if that command pushes the aircraft past its structural limits or into a stall.
And instantly, physics takes over. When the FACs lost power, the yaw damper died. And without the autopilot and an alternate law, the rudder unexpectedly deflects 2 degrees to the left.
Now, 2 degrees sounds negligible, but at high altitude, in thin air, flying near the speed of sound, a 2-degree slip on the vertical tail translates into an aggressive aerodynamic roll.
The massive A320 starts banking hard to the left.
Yeah, it reaches a severe 54-degree angle of bank. To put that in perspective, commercial flights rarely bank more than 25 to 30 degrees during normal passenger turns. At 54 degrees, the aircraft is practically on its side.
And with the plane suddenly rolling so steeply and the autopilot off, human reaction time and spatial awareness become the sole factors keeping the plane in the sky.
And this is where we see a chilling detail. It takes 9 full seconds before the pilot flying responds to the right side stick.
9 seconds. I mean, that is an eternity when an airliner is rolling onto its side at 32,000 feet.
It's a textbook example of the startle effect. The human brain can only process so much novel information at once. He was likely startled, his attention pulled away by the flurry of warnings and the unusual attitude of the aircraft.
So when he finally snaps out of the startle, his reaction is what initiates this devastating overcorrection.
Right. He finally grabs the stick and rolls the plane aggressively to the right to counter the leftward bank, and he actually succeeds momentarily.
He brings the roll angle from 54 degrees down to just 9 degrees left, so the wings are nearly level again.
But that rapid rightward movement completely scrambles his vestibular system, his inner ear. We really have to look at the biology here to understand why he did what he did next.
The semicircular canals, right.
Exactly. They're filled with fluid. When the plane banked 54 degrees to the left, that fluid eventually caught up and stabilized.
Oh, I see.
So when he rapidly snapped the plane back to the right to level it, the fluid in his ear sloshed violently in the opposite direction.
Meaning his visual instruments are telling him the wings are mostly level, but his vestibular system is screaming to his brain that the plane is now banking excessively to the right.
He is experiencing profound spatial disorientation, an overwhelming physical sensation of rolling too far right. So relying on that false sensation, he overcorrects.
He slams his side stick back to the left.
Right, to stop what he thinks is a rightward roll. And the aircraft, now in alternate law where it obeys every command without question, rolls aggressively back to a 50-degree left bank.
And this leads us right into the climax of the disaster at 06.17. Because in his disorientation and panic, he isn't just moving the side stick left and right.
No, his grip on the stick is pulling backward. He is commanding a massive pitch-up.
The pilot flying pulls back on the stick, and the massive jet rockets upward at a terrifying climb rate of up to 11,000 feet per minute.
It shoots from its cruising altitude of 32,000 feet up to roughly 38,000 feet. The pitch reaches 24 degrees nose up.
Which is insane for a passenger jet. You cannot climb like a fighter plane in the thin air of the upper atmosphere. The plane is bleeding off vital forward speed.
If we connect this to the bigger picture, you have to look at the tragic lack of coordination happening right now. The captain verbally commands, pull down, pull down.
But the pilot flying continues to pull backward on his stick. The angle of attack, which is the angle of the wings relative to the oncoming air, reaches a severe 48 degrees up.
The wings stop generating lift and start acting like giant flat air brakes. And at 06.17.117, the stall warning blares.
And this is where the design of the Airbus side sticks becomes critical, right? They are independent.
Exactly. In older aircraft designs, the flight controls are mechanically linked. If one pilot pulls back, the other pilot's controls physically move back too. You get immediate tactile feedback.
But Airbus uses a fly-by-wire system. The side sticks aren't connected to each other. They are connected to computers.
So the captain pushes his stick down to lower the nose and break the stall.
Yeah.
But the pilot flying is still mostly at maximum pitch-up. The inputs completely contradict each other.
So what does the computer do?
Its logic dictates that it averages the commands. The captain's nose-down input is entirely canceled out by the other pilot's nose-up input.
Meaning they're essentially frozen in a tug-of-war until the end of the recording. And because the plane was pushed into a prolonged stall beyond the crew's ability to recover, gravity takes absolute control.
It has lost the forward momentum required to keep air flowing cleanly over the wings. The aerodynamic lift completely collapses.
Looking at the final numbers, it is just harrowing. At 06.17.41, the plane reaches its peak altitude of 38,500 feet and a massive roll angle of 104 degrees to the left.
It is literally inverted on its side, and then it simply falls out of the sky. The initial descent rate is up to 20,000 feet per minute straight down.
But the wings do eventually level out, don't they?
They do. By 29,000 feet, the wings level out and the pitch angle drops near zero. But the plane is not flying forward. It is trapped in a flat stall.
Meaning it's moving forward at only 100 to 160 knots.
Which is nowhere near enough velocity to generate lift. Its angle of attack remains locked at a constant 40 degrees upward. The nose is level, but it's pancaking vertically downward.
It just falls at an average of 12,000 feet per minute until it impacts the Java Sea.
Yeah. The jet engines simply don't have the thrust to push the aircraft forward and out of a stall that deep.
So what does this all mean? We've traced the entire timeline. A piece of cracked solder triggered an annoyance. Unresolved maintenance issues led to repetitive faults. Then a pilot tried to use a ground fix in the air, changing the plane's computer logic. This handed a suddenly unstable plane to a startled crew, resulting in spatial disorientation and fatal contradictory stick inputs.
The overarching lesson here regarding the intersection of complex automated systems and human psychology is profound. The crew couldn't manage the aircraft once it departed the normal flight envelope.
Because modern airliners handle routine situations so seamlessly, pilots spend most of their time monitoring systems rather than physically flying.
Exactly. And when automation drops out, it usually happens when the aircraft is in a precarious state. The crew has to transition from passive managers to active pilots in seconds, often while fighting massive sensory illusion.
It leaves you with a final thought to ponder. In an era where machines handle most of the flying, how do we ensure humans are prepared when the computer suddenly hands back the controls in an emergency?
That's a critical question.
If a manual doesn't explicitly state the consequences of pulling a circuit breaker, should we expect a human under immense pressure to guess the outcome? We started this deep dive talking about a cracked piece of solder, a physical flaw so microscopic it evaded detection. But it was enough to shatter the delicate illusion of perfect control between human and machine. Thank you for joining us on this deep dive.